All right. Well, I will get those quizzes graded as soon as I can. I want to go ahead and make sure you're aware. Remember, tomorrow, not only is it a late start Wednesday, but what's happening? It's goals day, so you have a half day. You're going to be scheduled out or dismissed at 12:40. Here's the schedule. I went ahead and posted it to the website, so we'll still start at 9 o'clock, the normal time, but you'll be getting out at 12:40, and you're only going to go to periods 1 through 4, so I won't see you again until Thursday. Okay. So want to make sure you enjoy your half day off tomorrow. But what I want to go ahead and do, McKenna? Well, we're taking attendance each class period, so. All right. Okay. All right. So let me see if I can catch up the folks who weren't here yesterday. We seem to be doing all right with the chi-squared test for independence so far. So this is another test where you're going to have a null and alternative hypotheses comparing two quantities, two sets of data. Now, the data is going to be provided to you in what we call a contingency table. It's going to look just like this. They're also referred to as two-way tables because each group is going to be further divided into smaller groups. Like in this case here, we have gender. They divided it up into male and female. Okay, so you're comparing these two subgroups for the two main quantities here. Now, if you go ahead and take a look at what we've got, let me go ahead and erase all this because we were talking about it yesterday. But you have a grand total in the very bottom right of all of your, oh, everybody, you okay? Okay. So, okay. So in the bottom right of every one of your contingency tables, that is the total number of participants, total number of items that you have in your survey. So here, for example, let's say I want to know the number of males who don't exercise regularly. So what you want to do is just go ahead and match up the row and column to intersect at a particular value. You'll notice that each row has a grand total. The males have a total, the females have a total, and you also have column totals. So 216 plus 184 will give me 400. 208 plus 192 should give me 400. So you're matching up on the number of items that you have here for your total sample. Yes, that's exactly right. So let me go ahead and highlight that. So this right here, that represents one sum, while this right here represents another sum. But that last row and that last column, they both total 400. So that should always happen with these types of tables. Okay. So this test is designed very similar to the t-test to go ahead and help you decide which of the two statements, your null or alternative, that you're going to accept. But here, it's a slightly different idea. We're not comparing the means as in a t-test. We're comparing whether or not these quantities are independent. That means there's no relationship between the two of them, or they are not independent. You could say dependent. That means there is some relationship. In some way, one kind of influences or somehow is connected to the other. It'll simply tell you basically yes or no. Now, the drawback to the chi-squared test for independence is that while it will indicate whether there's a relationship or not, if there is a relationship, it's up for you to determine what that relationship is. So through your analysis, whatever it is you're comparing, etc. Now, when you're first provided your data, we call this the observed data. Okay, this is the data that was originally collected. Okay, so I've got 216 men, 184 females, okay, for 400 people total. Okay, now the first thing we started looking at yesterday, there's what we call the observed data, the original data, but there's also what we call the expected data, the expected frequency values. Now, what this means is this is the number that we would expect to see if there was no relationship between the two quantities, if they were indeed independent. And it's a really easy way to go ahead and figure it out. What you go ahead and do is you take the column total, multiply it by the row total, and then you divide by the total number in the survey. Okay. So let me go ahead and show you where some of these came from. Let me go ahead and highlight this one right here. Okay. So let's say I want to know the expected number of males who exercise regularly. Okay. Well, you'll notice that particular column total is 208. That row total is 216. Let me go ahead and erase that. That was an accident. Okay. So see this cell right here, that's the intersection of those two. So I want to take those two totals. I want to go ahead and multiply them. So 208 times 216. And then I want to divide by the total number in the survey. So let's see if I do indeed get 112.32. Okay. So I'm going to come on over here. I've totally forgotten the numbers, 208 and 216. So control divide, 208 times 216. And I want to divide that by 400. So control enter. See, there's the 112.32. So I would expect to go ahead and see about 112 men who exercise regularly if there was no relationship between gender and basically how often you exercise, if they were independent. Okay. So for the ladies who weren't here yesterday, help me out with another one. Let's say I want to go ahead and determine what the expected frequency value is for females who don't exercise regularly. Okay. So 192 times what? There you go. Okay, so let me go ahead and highlight these. So 192 and 184, they intersect in the one cell that I'm interested in. And you'll notice we've already got that right here. 192 times 184, again, divided by 400. That should end up giving me 88.32. Well, let's see if that's actually what happens. 192 and 184. So control divide. 192 times 184, and then we want to divide that by 400. 2208 divided by 25, control enter, 88.32. Okay. So we have the original data, which is the observed frequency, and then we have the expected frequency, which is how we calculate this. This is what we would expect to see if there was no relationship between the two quantities. Okay. So are there any questions about that? Okay, so why don't we go ahead and practice that a little more? I think that'll probably be the best thing right now. We did go ahead and see our first problem yesterday, and here's the formula, but we're going to go ahead and skip that right now. We'll come back to that. Okay, let's say I wanted to construct an expected frequency table for the following contingency tables. Okay, now they don't give me the original data, and I don't need the original data to find the expected frequency values. Let's say I want to go ahead and find the expected frequency for the number of people who like fish and like chicken. Okay. So what am I going to multiply to make this happen? There you go. So let me go ahead and erase this. So this one right here would be 75. So 75 times 60, and then I'm going to divide that by what? How many people were involved in the sample? 100. Remember, in the bottom right corner, that's always the total number of participants. So we'll come back and we'll calculate that in just a second. Let's say I want the expected number of people who like fish but dislike chicken. Okay, so 25 times 60, again, divided by 100. Okay, what if I want the expected number who don't like fish and then likes chicken? 75 times 40, and then we'll divide that by 100. So is everybody okay with how we're calculating the expected frequency? Okay, so it's pretty easy, pretty straightforward. Then everybody would agree for this last one here, if we don't like fish or chicken, 25 times 40, we're going to divide that by 100. Okay, all right. And I don't know how some people don't like fish. Maybe they just don't like it for the halibut. Or the halibut. I don't know. Maybe it was an act of con. I've always got jokes. There we go. Okay. All right. So here's what we should be getting. If you go ahead and put these in the calculator, the expected frequency values, this one's 45. This one is 30. This one should be 15. And this one right here should be 10. Oh, guilty as charged. I'll stop. Okay. All right. So is everybody getting the idea? Oh, there we go. Any more? Oh my goodness. And we haven't even said any chicken jokes yet. I mean, what the cluck? You know, I just said that and I immediately regretted it because I'm recording. So, yeah. Anyways, there's another one here. Exactly. Okay. So this one here is whether or not a student plays sports and what level of school they're at. Okay. Which is kind of weird to me because I've always thought of junior and middle school as the same, but here they're making a distinction. Now, let me go ahead and ask you, do we want to go ahead and continue to practice finding the expected frequency values, or do we think we're okay with that? We feel okay? Okay. Well, at the very least, because I'm not going to see you for a couple of days, let me go ahead and make sure that we're familiar with the formula. Okay. Now let me go back to the original page right here. Okay. Yeah, remember tomorrow's a half day. Yeah. No, because 2 days from now will be Thursday at the end of school. Am I wrong? Okay, so make sure. I know it's gonna be a long time before I see you again. So, yeah. Sad. Okay. All right. So you remember I called this the observed data. Well, we have a notation for this. It's F naught. So it's F with a little subscript 0. That's just the observed data. Okay. So basically F sub 0. I always say F sub 0. Technically it's an F sub O, but F naught, I always refer to it as a 0. So that's the observed data. So the expected frequency data, which we found here, we call that F sub E. Okay, so the formula that we're about to look at is going to make a lot more sense to you. So using these values, here's your formula. Okay, so what we want to go ahead and do is come up with what we call the chi-squared calculated value. So this right here, this notation, it looks like the fancy x squared. That's our notation for chi-squared. And we have the subscript calculated. So does anybody remember chi? Chi. Chi-squared. Does anybody remember what does sigma tell me to do here? That's the sum. So this is the symbol we use in mathematics for summation. So this is telling me to take the sum of this right here. So one of the things we did yesterday was we went ahead and looked at a problem where each column was progressive moving towards this particular formula here. So you'll notice we'll have a observed data column, we'll have an expected frequency column, we're going to subtract them and square them, and then we're going to go ahead and divide by that observed, or from the expected data. So here's the example that we did yesterday, and we'll go ahead and do another one come Thursday. But you'll notice here's the observed, here's the expected frequency. We subtracted them. We then went ahead and squared them, and the final column is the formula here. But remember, we want to take the sum of all of those values. So that's down here at the bottom. That's how we ended up with a 0.217. Okay. So see, my original values were 110, 106, 98, and 86. Those were the number of people observed exercising or not exercising regularly. Here are the values that we calculated for the expected frequency, and we just, bless you, applied the operations. Now, there is something specific what we're going to go ahead and do to make sure our analysis is accurate, but in the beginning, this is how we're going to go ahead and tell whether to accept or reject the null hypothesis, okay? If your chi-squared calculation is really small, well, then we're going to say they're independent. That means there's no relationship. Okay. Conversely, if we get a larger chi-squared calculated value, okay, if it's larger, that means they are not independent. That means there's some kind of relationship. Remember what I said in the beginning, though. This is really good at telling you whether or not they're related in some way, if there's some relationship, but it doesn't tell you what. That's exactly right. It doesn't tell you the relationship itself. That's still up for you to go ahead and decide what you believe it is. Okay. You sure? Okay. All right. So we'll go ahead and start looking at some examples, and this will start making a lot more sense come Thursday. Okay. Yes, because Jorge had a great question yesterday. His question was, well, how do we know at what point it becomes too large and we go ahead and switch between the two? There is a value that we're going to find called the critical value. This is what you're going to compare to your calculated value, and that's going to help us decide between our two hypotheses. Okay. No, it changes based on your significance level and what we call degrees of freedom. But I will explain what that is on Thursday. Okay, so I'd say that's a pretty good synopsis for what we had today.